Hello, it's Keith here, and this is lesson 3 of the so-called MinTile series of my 650 assembly programming tutorials, in which we're looking at this multi-platform software tile map example. It's a software tile map on the systems that only have bitmap screens. It's a hardware tile map on the systems that have a tile map screen. And so we've got this example here. You can see we've got a background. If I press the 5 button, I think it's Control, we can scroll the tile map, and we have these little characters moving around the screen, which I'm going to refer to as sprites, and some smartass will point out in the comments that they aren't sprites, because sprites are a hardware thing and anything software is not technically a sprite, and I don't care what they say because they're a smartass and it's not relevant. The point is we're going to create a bitmap tile map on the screen, and we're also going to create movable objects, which I'm going to refer to as sprites, but they're actually being created with the same tile map code, by which I mean on the bitmap systems it's the same tile map drawing routine that draws those sprites onto the screen, and on the systems that have a hardware tile map, in most cases it's the tile map drawing the object within the same 8x8 pixel block boundaries. It's being drawn onto the tile map rather than using hardware sprites. The reason for that is it's simple. MinTile is a minimal tile map. It's designed to be simple and basic, but work in a multi-platform way. Now, the only exception to that is some systems like the NES can't flip the tile map, so we are using hardware sprites where we're doing the X-flip effect, but generally speaking, as a rule, I'm not trying to use hardware sprites. But as I say, I am going to refer to the object as sprites for convenience, because most people understand a sprite to be a movable object. Anyway, what we're going to look at today is how we're dealing with removing the sprite when it's moved around the screen. If I hadn't closed my example there, it was wearing my fans quite a lot, but if I hadn't closed it, we would see that when we move our sprite object, our little Chibico character at the top there, the background is of course having to be redrawn, and you can see some flickering around the edges as it's being redrawn because we are not using a double buffer. So another thing of the MinTile is one of the specifications of when I designed it was it couldn't use a double buffer. The reason being some systems haven't got very much memory, so a double buffer is a luxury we may not be able to afford. So let's assume it's not there and try and do our best without it. So let's go to our code and let's take a look at the parts we're going to look at today, which is the sprite removal code, and also the code that actually, some of the helper code that it invokes to do some mathematical operations with regards to working with the tile map. Okay, so we're going to run this remove sprite routine, and this is basically going to force a redraw of the tiles underneath the sprite, overlapping the sprite object on the bitmap screen, or on the tile map screen it will redraw the tiles, because as I say, the sprite object is actually drawn with tiles on the systems that are hardware tile sprite. As I say, at this stage I'm just doing the simplest thing, which is to use the tile map. So that's what we're going to do. Now, the first thing we're going to do, when this is called, all of the 0-page entries are simulating Z80 registers. This is a multi-platform piece of code. It exists on the Z80, 6502 and 68000, and it was ported from the Z80. So the IX pair is IXH and IXL, and this is a 16-bit pointer to the attributes of the current sprite object. And one of those attributes is the refresh tile flag. This defines if the object needs to be redrawn. If it's moved, we need to redraw the tile map, and that flag will be set, but if it's not set, we're simply going to return and give up. Okay, so we're going to now redraw this object then. So what we're going to do is we're going to load in the old position of the sprite, the position that we want to delete because the sprite is now somewhere new. We're then going to load in the width, and we're going to load in the height. And what we're doing here is if we're allowing the object to move in fractions of a tile is 8x8 pixels, but we could move in a 2-pixel jump or a 4-pixel jump. We can't move in a 1-pixel jump because the coordinates are logical units, which I've declared as pairs of pixels, and that's so that the 256 by 192 screen is a 192 by 96 screen, and that it means the coordinates will fit within a byte with an area off the screen, the same as I did in my my sprite cropping tutorial. So that is the coordinate system I'm using in all of my stuff now. 2 logical pixels equals 1 logical unit, because the vast majority of 8-bit systems can't move with any lower definition, and as I say, it's very good for working in byte coordinates on these screens. Okay, so we're loading in our width and our height here, but if we are allowing those fractional moves, we need to basically expand the area by 1 tile so that we're covering the tile, because it will have moved 1/2 unit, and that means that it will have overlapped the next tile, but we still need to remove the original tile because it's now half in the first tile and half in the last tile plus 1 basically. So we're adding 1 full tile, 4 logical units, 8 pixels to the width and the height here. Now we are then going to basically run our cropping routine here, this is calculating for if our object is partially off the screen. Because if our sprite is in a position like this, well, we don't need to redraw the entire size of the sprite because half of it's probably off the screen. So yeah, we only want to redraw the part that is off the screen, and we want to calculate the appropriate coordinates. So we're doing that. We're not going to deal with any flipping though, because it doesn't matter to us at all whether the sprite's facing that direction or that direction. The area it's covering is exactly the same. So we're just doing the unreversing version that just deals with the sprite size. And then we're going to run this routine called do crop logical to tile. Now basically all this does is it divides the width and the height and the x position and the y position by 4. But one thing it does do is if the width or the height becomes 0, maybe the width was 3 logical units, which is just 6 pixels, which is less than a single tile, well, now there's nothing to draw. So it will basically set the 0 flag, and if either the width or the height is 0, we will have the 0 flag set, and we would just return because our sprite is not drawable. It must be entirely off the screen, at least in full tile units, because the code, being minimal tile code, being simple code and optimized for some of these 8-bit systems, it can draw one single tile if there's only a single tile. But if there's just half a tile on the screen, it will draw literally nothing. That is another limitation of the MinTile. So in that case, we're just returning. Okay, so now what we've got is we've got our width and our height. So we're transferring those from H and L to IXH and IXL here. Those are the parameters we're going to use for this part. Now what we're going to do next is we're going to be basically having to transfer our tiles into what's known as the tile cache. Now this is an update cache of the changes that need to be made to the visible screen. As I say, we've only got one screen buffer in bitmap terms, but we have a tile cache, which is the requests for the draws that need to be done to the screen. This is 32 tiles wide, which is hexadecimal 20. So that is the width of the tile map that is the cache that we're going to be transferring to. Now that is the cache of the changes, but we have a second tile map. We have something referred to as tile map 2, and this is the actual background that is being shown on the screen. So the cache is the changes, but the tile cache 2 is the actual background. And you saw before I was able to scroll up to 4 tiles. So the actual tile map 2 is actually 36 tiles wide. That's 4 tiles more than the 32 tile wide screen. So that is being loaded in here. That is the source tile data that we will want to draw back to the screen. And that is 24 in hexadecimal wide, which is 36 tiles wide. So we're loading that in there. Now we're adding the offset. This is the X scroll position. We are rounding. We're taking only the bottom 2 bits of the offset because that is the tile offset to the tile map itself, because as I say, there are just 4 tiles that are spare within that are not visible on the screen at all times. 32 tiles wide screen, 36 tile wide tile map, and so there are 4 tiles spare, if you will, and that is the offset for that. We're then adding that offset here, and we're going to run this shift tile map routine. Now what the shift tile map routine does is it takes our X and Y position of our sprite. There's my sprite, here it is. So if our sprite is here, we've loaded in the start of the tile map address, which is the top corner here. Now what we want to do is we want to shift that memory address here to point to the top corner of the actual sprite. Now we'll need to do this in 2 cases. Now the first case that we need to do it is actually to the tile cache itself, and we're doing that to the tile cache here, which specifies the position within the cache of the draws that need to occur. But we then need to do it to the original tile map as well, which we do here, and that is because we need to work out what tiles are under the sprite, what graphical patterns need to be drawn back into the tile cache to actually show the background that the sprite was previously containing. And so we're doing that there. Now what we're going to do next is we're basically going to start transferring the data from the original tile map 2, to the tile cache. Now the tile cache is 32 tiles wide, 20 in hexadecimal, and what we're then going to basically do is we're going to do a sequence of LDIR commands. This is a Z80 command that has been recreated. Basically what it will do is it will transfer BC in the 0 page bytes from memory address HL to DE. Now DE is going to, at this point, be defined as the tile cache. It's been calculated here, and it's been stored to the tile cache in DE here. So the DE is the tile cache. HL, the source, is the actual tile map, which is the original data. And so the LDIR here will transfer the number of bytes only that are contained within the sprite. So we're only redrawing the area that the sprite is actually containing. So if it's almost entirely off the screen. We're only going to draw the area on screen, and that is being loaded in. The width here is being loaded in by IXH, and one line is being transferred by the LDIR command there, that subroutine there. And then after we've done one line of our sprite here with that command here, what we're going to do next is we're going to basically update our source data. And so what we're doing here is we're basically adding the width of the tile cache, so 32 tiles, and we're adding that to the current position within the tile cache that we're drawing to. So we're effectively moving down one full line, and we're going to start with the next line of our sprite. So we're still working on the sprite area, but we're moving down to the next line like that. So that's doing the destination DE here, and then we're doing the HL source here. So we're adding the width of the tile map here, which, as I say, is 36 tiles, to the tile map here, and then we are decreasing the counter for the height of the sprite, and we're doing the next line, and that's so we're just doing the area that the sprite is actually overlapping, and then we return. So that is how we are removing our sprite, transferring the original tile patterns from the tilemap2 object into the tile cache, which is the update cache, which is drawn to the screen via the CLS routine, which we saw before. Now, that is going to use some routines that help it out. Now, one of these is the ShiftTimeUp routine here, and what this is simply going to do is it's going to take the source tilemap in DE, the X and Y position in BC, and it's basically going to shift down to the correct position within the tilemap for that XY position. So basically what we're going to do here is we're going to add the width of the tile map in IYH to the memory address of the tile map, which is now in HL. It was in DE, but we switched it up here. So it's in HL now, and we're adding the width of the tile map for the current Y position repeated. So this is kind of like a multiply routine. So if we're 5 down and our tile map's 32 wide, we add 32 5 times, and that is calculating the memory address of the start of the line that our sprite is on. And then what we're doing is we're adding the X position of our sprite in tiles, and so our memory address was pointing to here. We've now added the X position in tiles, so we're now pointing at the very top left corner of our sprite object that we want to remove, or whatever we were calculating this tile map for. As I say, that's what we use it for. And so once we've done this, we've now calculated, now in HL, it was in DE and it's now in HL. And you might say, well, why is that? And the most honest answer is that this is ported from the Z80 code, and it made sense in the Z80 version. And for two reasons, I keep things the same on the other systems where possible. First reason is it's quicker for me to port if I'm keeping things working the same with the same, I'm using Z80 registers and zero-page entries with the same kind of names. It makes things easier to debug, and it makes it easier to keep the code consistent. So, to say the porting is better for porting, and it's better for working with it later. So there are two benefits, especially when I'm working with so many systems. So that's why sometimes you might think, well, why are you doing this? Why are you using this EXDHL thing? That doesn't exist. Well, true enough, but as I say, when it comes to finding a bug in the code, if the code matches as close as possible to the Z80, and I know the Z80 works, it makes it a lot easier to fix problems in this version, and in some cases port corrections back as well. I found a bug in the code when I was doing the 6502 version, ported it back to the Z80 version, and again, it's easy to spot if the code looks as similar as possible. Okay, so that's one routine. Another one, as I mentioned before, is do crop logical to tile. Now, all this does is it takes the logical units, which is in pairs of pixels, and converts them to numbers of tiles, which are in 8 blocks of pixels. So basically, we just divide by 4, and we just do that by logical shifting to the right. So we're dividing our X pos, our Y pos, our height by 4 here, and if that's gone to 0, then our height is 0. There's nothing to draw, so we return here. We're jumping down and returning, and then we're doing our width. And in the way we've done it, basically, if the width or the height is 0, we're setting the 0 flag and returning, and so that allows our calling routine to know that there's nothing worth drawing and it should give up. Now, the last one we're going to look at is ChangeScroll. Well, what does ChangeScroll do? Well, this is a routine that helps out with regards to the fact that we don't have a double buffer, as I said before. So as you can see here, we've got our test graphic on the screen here, and as I say, if I press the control button, we've got this scrolling here, and you can see that the screen is scrolling across. Now, on a bitmap based system with a relatively slow processor, that's a lot of pixels to get back on the screen, and we really don't want to have to try and push too many pixels because we haven't got much CPU power. But we're moving in full tiles in this example, so we're never moving in a half tile scroll, and that means that if you look at the tiles that are being drawn to the screen in between scrolls, well, actually a lot of them are the same. You know, it looks like all the tiles are scrolling, but a lot of them are the same as the tiles that were there before. Well, why would we draw those again to the screen? Well, if we're smart, we won't. And so that's what this routine is going to do. ChangeScroll is basically passed two memory addresses to the of the source tile map, BC and HL, and these will usually be one tile apart. So if we're scrolling, this is maybe the first scroll position and this is the second scroll position, and what it does is it compares the two, and if they're different, then we need to update the drawing to the screen, and so we need to write that to the tile cache. But if they're the same, then the old scroll position and the new scroll position are showing the same tile in the same position, and there's nothing to do. So we won't do anything, and that saves us some speed, which is very good. That's how we get that nice fast looking scrolling with only a single buffer and not too much flicker. So that's all good. So what we're doing here is we're comparing the two positions in the source tile map, and remember it's the same tile map. This is tile map 2, the actual tile data that we want to draw to the screen, not the cache. And so we're comparing them, and if they are the same, well, the screen is showing what we want it to already, so nothing to do. If they're different though, we're storing the value that was loaded from BC to the tile cache in DE here, and so that is forcing an update of that next time. We're then incrementing all of those all of those memory addresses, BC, HL, and DE. We're then decreasing our width, and we're just repeating. Now, once we've done a full line, we need to actually update our HL and BC tile maps. Those are tile map 2, remember, and that is 36 tiles wide, even though the cache is only 32 tiles wide. So there's a discrepancy of 4 tiles, and that's why we're adding 4, skipping the 4 tiles that are not on the screen before we repeat, and then we're just repeating here. And that's how we're basically doing that comparison. And as I say, before I did that, you would probably, with that the screen example that I showed there is very simplistic. There's a lot of repetition, so it's going to get a good amount of efficiency, but we're probably saving 3/4 of the time on that tile map. And as I say, while it's a very simple tile map games on 8-bit systems tend to be very simple, to be honest. The vast majority of Amstrad CPC games that use tile maps, they were very small indeed, because the system wasn't good at, it didn't have any hardware scrolling, and the screen was very memory intensive, and so a lot of the games, they would shrink the screen to 256 by 192, and then they would have the screen wouldn't be the full screen either. So as I say, they're very good games, but it's very rare to see a full screen, even 256 by 192 scrolling game on the Amstrad CPC. So while the code is showing a fairly simplistic example of a scrolling background, it's not that unrealistic for the kind of games you would see on that system. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.